pleased to introduce the speaker for this session, Eric Nielsen. Eric is a senior research scientist with the Computational Aerosciences branch at NASA Langley Research Center in Hampton, Virginia. He received his PhD in aerospace engineering from Virginia Tech and has worked at Langley for the past 30 years. Dr. Nielsen specializes in the development of computational aerodynamic software for the world's most powerful computer systems. The software has been distributed to thousands of organizations around the country and supports major national research and engineering efforts at NASA, in industry, academia, the Department of Defense, and other government agencies. He has published extensively on the subject and has given presentations around the world on his work. He has served as the principal investigator on agency-level projects at NASA, as well as leadership class computational efforts sponsored by the Department of Energy. Dr. Nielsen is a recipient of NASA's Silver Achievement, Exceptional Achievement, and Exceptional Engineering Achievement medals, as well as NASA Langley's HJE Reed Award for Best Research Publication. It will now be our pleasure to hear from Eric Nielsen.
So good afternoon. My name is Eric Nielsen. I'm from NASA Langley Research Center. That's on the East Coast of the United States. Let me start off by just saying thank you to the organizers for inviting me. I see a lot of interesting talks on the agenda today, and I look forward to taking some of those in over the course of the day. But I've been asked to come in and speak a little bit to the role of emerging architectures for both capacity and capability class CFD simulations, or computational fluid dynamics. So that's what we'll be covering for the next few minutes. First, let me go back about 20 years, and if you were to look at the front page of the New York Times in April of 2002, you would see this article right on the front page with a headline that says, "The Japanese computer is the world's fastest as the US falls back." The first sentence in that article read that a Japanese lab has built the world's fastest computer, a machine so powerful it matches the raw processing power of the next 20 fastest American systems combined. These were pretty hefty words at that time. It was a real kind of wake-up call for the US supercomputing community. The article goes on to quote some American computer scientists who even likened this to the alarms raised by Sputnik in 1957. So again, these were pretty hefty words that appeared in the New York Times that day. This is the actual system up here, a picture of it. It's the size of 2 tennis courts, essentially, known as the Earth simulator. And that Earth simulator was capable at that time of about 36 teraflops, okay, or 36 times 10 to the 12th operations per second. And so kind of keep that number in the back of your mind as we go through the presentation. I'm going to kind of revisit that here and there. But 36 teraflops in 2002 on this largest system out of Japan. Okay, about 8 or 9 years ago, NASA Langley commissioned a study known as the CFD Vision 2030 study. And this was run out of Boeing with help from many folks in industry and in academia and the broader community. And essentially the study was commissioned to identify the technologies and a path to further develop them so that the community could accomplish the goals that we saw for the year 2030, kind of coming down the pipe. And so this kind of roadmap that you see here on the screen is kind of the iconic image that came out of that report. And it identifies several swim lanes for various technologies, but you see across the top there, high performance computing, or HPC, was recognized by the committee at that time as the overarching technology that would enable realization of all of those other technologies. Okay, so here you see HPC playing center stage in this particular study as we march as a community towards the year 2030. And so that kind of puts in perspective or relevance why we're kind of here talking about this particular topic today. Okay, capacity versus capability class computing. I've got a cartoon going across the top of the chart here. On the far left end, you can think of this as very low fidelity simulations. So in CFD, you might think of the Euler equations or Reynolds average Navier-Stokes, for example, where we do a lot of modeling of certain terms. As you march to the right, we pick up more and more physics, eventually going to something like a direct numerical simulation where we eventually get rid of all of our modeling and turn to the numerics to resolve all scales. But obviously, as you move left to right, there's a tremendous amount of computational cost that comes with that. So that's kind of the predicament that the engineer and scientist are in on a day-to-day basis. If you look at today's engineer in his cubicle, kind of do an aircraft design, for example, typically that engineer will rely on simulations based on the Euler equations or Reynolds average Navier-Stokes, and he's often running on maybe several hundred CPU cores for a few hours at a time, perhaps, to get one solution. Okay? On the other hand, the CFD Vision 2030 study calls for the prediction of unsteady separated flows. So we know how to predict drag, for example, on a 737 in cruise across the country. Where CFD has a real hard time still these days is the edges of the flight envelope. So consider takeoff and landing or the high lift scenario. In those cases, unsteady separated flows are very important to capture accurately. And unfortunately, our conventional methods fall flat there. And so we need to progress more towards the right end of this spectrum in order to go after that level of physics. Okay? And again, unfortunately, that comes with considerably more computational cost. Okay? Now, we've seen exciting advances in hardware over the last decade or two, and they're having a substantial impact on both of these scales, both the engineering class computations as well as kind of the leadership class computing scales. And so that's the good news. The kind of not so good news is that the new advances in hardware have brought a tremendous burden on the application developers. So our colleagues at the Department of Energy and in many of the vendors, 10 or 15 years ago, sat down and looked at what kind of hardware paradigms do we need to be looking at in order to continue this constant progression of computational capacity, year over year, decade over decade. And generally what they found was that power was the limiting factor at that time. So if you tried to build an exascale supercomputer out of the technology of that time, your power bill would be prohibitively expensive. So what the community has kind of progressed towards over the years is a paradigm in which we have much more concurrency, perhaps running at slower clock rates with many, many more processing elements. Okay, and in that manner, we're getting much more computational throughput at reduced power requirements. Okay, and it's going great in that regard. Again, it's just a tremendous burden on the application developer to port a legacy application of perhaps millions of lines of code from something that can run on yesterday's architectures to something of this kind of class, one of these newer emerging types of architectures. Okay, so when we look at the field of HPC, often three areas are identified as being critical to having success here. The first I'll talk about is workforce skills. So I sat down with NVIDIA at Supercomputing in 2010 and quickly realized that NASA did not have the workforce skills in place to be able to develop code for these new architectures that were going to be coming down the pipe in a decade or so. So the first thing we had to do was kind of get out there in the community and partner up, kind of get a coalition of the willing, people who are willing to hold our hands, come alongside us, and help us climb this steep learning curve as we learn how to use these new hardware architectures. And as we did that, we start to be able to explore the various nascent programming models that were available at the time. But along the way, your organization has to buy in, right? This is a long-term investment. It's a pretty heavy lift, again, to convert a code from kind of the old architecture to one of these newer architectures. So you have to have a substantial software development kind of plan in place that allows us, for example, to go back and learn how to do matrix vector products on a GPU. That sounds trivial, but it's surprisingly, deceivingly difficult to do very, very well on one of these new architectures. And then progress kind of up the ladder there, bringing more and more complex algorithms and learning how to mate those up with the hardware and the memory hierarchies and stuff like that. And then finally, you got to have the hardware come along. And obviously, this is a very NVIDIA-centric chart here, you might say. But if you look at the hardware side of things, it's amazing to see how technology has moved over the last decade. It's really remarkable how much has come online from the hardware perspective. And so hopefully, at the end of the day, if you can get kind of these three areas to converge eventually, the hope is that you will be able to realize, a next-generation leadership class performance potential. And so that's what we'll kind of talk about over the next few charts. But that's kind of where we've been over the last decade or so. Okay, so our code at Langley is known as Fun3D. Our GPU-enabled version of that code has been used internally now for both capacity and capability class simulations since about 2018, several years ago. And so if you look at a cartoon like this on the right, this is real data, but essentially if you look at a conventional compute architecture such as a Xeon Skylake dual socket processor, a Cascade Lake, for example, and then compare that with our performance on something like an NVIDIA V100 or A100 GPU, you can start to see that you get speedups of roughly 4 to 8x going at device level, head-to-head, CPU versus GPU kind of thing. And so you can start to do some thought exercises here in terms of how can I bring that to bear for capacity compute scenarios. And so this is an example here I pulled out from our colleagues at Ames. When the aerospace community kind of fields a new vehicle, we often develop what's known as an aero database. So we identify all these points in the flight envelope where we would like to understand the aerodynamics real well so that we know how the vehicle is going to fly in those situations. And so what this basically consists of is thousands and thousands of CFD simulations. Okay? Now, in and of itself, one simulation may not be that expensive. But again, if you're doing 10 or 20,000 of these things to develop this database, now you're looking at a pretty substantial investment in terms of human time and compute and things like that. So you can start to think now, can I go to, in this case, the Space Launch System, can I go to the program manager and say, how would it help you? How would it impact your time frame or your planning if I could deliver that database in a week or in several days instead of several months? And so therein kind of lies the long-term goal of what we're trying to do here and bring these emerging architectures to bear on capacity class or engineering class simulations like this. Okay, I'll give you a quick example, again from the Space Launch System here on the far right. All three of these stories are kind of parallel and analogous in nature, but let me just kind of hone in on the SLS here on the far right. The first way we can look at performance is just kind of a node level comparison. Okay? So first we ran this simulation on 11 nodes with 6 V100s. Okay? And so we can turn around that simulation in about 17 minutes on that amount of hardware. And then what we did was we took 11 nodes of kind of conventional dual socket Skylake Xeon processors, and that same simulation takes about 7 hours in that environment. Now, that's how you arrive at these astronomical speedups of, say, 25x, between kind of the conventional way of doing things and some of these newer architectures. But any person can quickly look at this and say, okay, that's not a level playing field, okay, in terms of cost or power or anything like that. So typically what we do in practice is we will do that simulation on the GPUs, in this case 66 V100s, and then we will dial up as many CPUs as is necessary to keep pace with that GPU-based simulation. In this case, we found that it took 350 nodes of dual-socket Skylake, or about 14,000 cores, to do the work of 66 V100s. And so you can start to do some back-of-the-envelope math there in terms of price, performance, space savings in your data center, power costs, for example. And so you can start to see a case there in terms of the conventional computing technology versus the newer kind of GPU-based approach. So just in a nutshell, that's what we see on a typical engineering class simulation at this point. Let me give you one more example. This is our Artemis system. We hope to launch here in the next couple of weeks, actually. But again, going back to the SLS, there was a situation last January where we were looking at like a March timeframe for launch at that point. And in January, they rolled the full stack out to the pad to do some tests and so forth, known as a green run. Well, when they brought the system back in, they realized that they had inadvertently done some damage to the thermal protection system right in the side of the center core stage there, where it happens to attach to the booster on the side there. Unfortunately, it's known that that area is very susceptible to aeroacoustic phenomena or vibrations. And so the program came to us in January and said, we need you in 10 weeks to understand the impact of that repair and tell us if that's okay to go forward for flight at some point. And so they gave us 10 weeks, and effectively what we did was we kind of commandeered all the available GPUs at our facility at that point in time, and we spent about 9.5 weeks doing high-fidelity simulations on those GPUs to try and characterize the environment there induced by that repair. And so we delivered that data back to the program, and they eventually determined that, okay, it was okay to go forward with flight and that it was going to be okay. But again, this is just an example story of where we've been able to bring some of these advances in hardware and algorithms and software development, kind of mate them together and realize a reduced turnaround for a real-world problem where we effectively got a 911 call on a very important problem. Okay. Outside organizations. We put this capability out in February of 21 after a delay due to COVID, but we immediately began receiving reports from these folks of substantial impacts on cost, facility, and power footprints at their organizations. Major impacts on contract awards, for example, with many of these groups. The engineers were telling us vast speed-ups in efficiencies for database generation for aero heating, and aeroelastic type simulations. And we are now fielding numerous requests for guidance on how to kind of revamp the procurement strategies for on-prem resources as well as adopting cloud-based strategies. Just a few kind of examples here in the upper right. This is some data that Rescale generated a few months ago, basically quantifying the impact on wall time and ultimately on cost as seen by the end user between the kind of original way of doing things and some of the newer architectures. On the lower left, this is an example from one of our earliest beta users from a number of years ago now, up at MIT Lincoln Labs. And so they were doing a lot of GPU-based simulations for full aircraft aerostructural flutter analysis and comparing those results with actual flight test results from one of their Gulfstream aircraft that they have up there. And then finally, recently we've been working with Sierra Space and their Dream Chaser vehicle. And they are trying to understand essentially aero heating in this case. Okay, so we're coming back to Earth, Mach 16, high angle of attack. The name of the game is predicting that heat load on the vehicle surface. So in this particular case, we've done the simulation with the unstructured grid kind of GPU-based implementation in Fun3D. And then plotted that against what is widely considered the gold standard kind of benchmark code for this space, known as DeepLR. If you're in this space, you've no doubt heard of DPLR. But effectively, that GPU-based simulation effectively sits right on top of the heat loads as shown by the benchmark simulation there. So now we've talked about the engineering class simulations or the capacity scale simulations. Let's scale up now and talk about leadership scale using these new architectures. In 2018, a system known as Summit debuted at Oak Ridge National Labs, and it was essentially built around NVIDIA V100s at its core. And this is the node-level architecture, and you can immediately see the challenges in programming something like that. We have to understand as developers, how do we traverse that complex memory hierarchy, talk to the neighboring processing elements, talk to the off-node processing elements. It's a tremendously difficult system to kind of adapt to from a kind of a conventional CPU-based facility. But the proof is kind of in the pudding, and we were very fortunate at the end of the day. When Summit was stood up, we were able to get on the system there, and in this case put a mesh of about 1 billion points on the system and run up to about 20% of Summit at that time, which was about 6,000 V100s. And effectively, you've got the CPUs running in blue and the GPUs running in green, and they both scale linearly as you would hope. But the offset between the curves is really kind of the punchline here. So this really kind of quantifies the turnaround time that we can have an environment like this. Okay, so using emerging architectures at scale and having that kind of relationship to hold all the way up to scale was very, very encouraging to see at the time. Now, let me kind of rewind to that original New York Times article I told you about in the first chart. We talked about 36 teraflops of performance on that Earth simulator in 2002. Well, by 2018, we now have node-level performance of 40 teraflops. In other words, one set of these 6 V100s on one blade in one rack is capable of what that entire Earth simulator could do in 2002. So again, keeping in perspective how quickly this state-of-the-art moves in this HPC space. And obviously 150 petaflops is a tremendously powerful system as an aggregate. Okay, how do we make use of a system like this at NASA? We're very grateful. We've partnered with Oak Ridge for a number of years now, and we are looking at retropropulsion for human-scale Mars landers. So these landers are the size of a 2-story house, unlike the small rover-class vehicles that we've taken to Mars so far. And so we need to look at some new technologies on how to successfully slow down before we reach the planet's surface. In this case, we're doing simulations of methane combustion in Martian CO2 atmosphere with roughly 15 partial differential equations on meshes of 7 billion elements. To give you a feel here, each simulation takes about 2 days, and that simulation uses about 16,000 V100s. Okay? To put that into perspective, that is the equivalent throughput of several million CPU cores in terms of computational throughput. Or put another way, if you give me a dedicated system of 100,000 CPU cores, I'm going to need to run for 2 months to do that same 2-day simulation that I can do on the newer architecture at scale. Okay? Big data, we're dumping close to 100 gigabytes of data every 30 seconds of wall time, asynchronously. And you do that for 2 days straight, and you end up with about a petabyte per run, or about 50 libraries of Congress, depending on how you kind of slice and dice the numbers there. But this is an example of how we're using emerging architectures at leadership class scales to go after some of the most challenging problems that we are facing at NASA. Okay, and again, I just want to hit home on this partnering deal. It's absolutely critical, again, that all these partners are here with us kind of holding our hand. We could not do this without everybody seated at the table. And in this case, 7 or 8, 9 years into our kind of move from the conventional approach to kind of some of these newer architectures, we got an interesting call from the team at NVIDIA, and heard that Jensen Huang wanted to tell our story on stage at a keynote he was giving in kind of front of a worldwide audience. And so we were very, very flattered to get our kind of science PI up there on stage, and her and Jensen hit it off real well for 10 or 15 minutes talking about Mars entry using petascale class supercomputing on new architectures. And so, but again, you know, all of these kind of capabilities only were able to come about because of all the people kind of coming alongside us. And so we're super, super grateful to all these organizations who have kind of helped us over the years kind of climb this steep curve. Now let's talk exascale real briefly here. Let's talk aeronautics first. Why do we need exascale for aeronautics? Well, when we talk to an aircraft manufacturer today, they are spending $1 to $2 billion to certify a new commercial aircraft for service. Okay? And much of that budget goes to the high lift portion of the flight envelope, takeoff and landing. Can we bring exascale class computing to bear so that we can do higher fidelity modeling and simulation to perhaps take that off of the flight plan, so to speak, and potentially save a company several $100 million in flight testing by doing it virtually inside a supercomputer? Okay, so there's an example from the aeronautics side. From the space side, when we send a new vehicle to Mars, for example, we have tremendous uncertainties there. We don't know what we don't know. And so we have to design a vehicle very conservatively. So for example, our thermal protection system, you know, maybe twice as heavy as it needs to be, the heat shield. So what does that ultimately, you know, mean? That ultimately means when we arrive at Mars, because our vehicle was not efficiently designed up front, we can do less science. We're restricted to less science on the surface when we arrive at our destination. So can we bring exascale computing to bear with much higher fidelity simulations to get a handle on those uncertainties and understand our bounds and so forth much better, so that we can design a much more efficient vehicle that can still arrive safely and allow us to do much, much more science when we get there. So again, but this is just the tip of the iceberg. So you start talking about uncertainty quantification, MDAO, robust design, actually flying maneuvers and trajectories inside virtually inside the supercomputer. We're really just at the tip of the iceberg. So we have plenty of plans to make use of exascale class supercomputing. And if you're familiar with the space, Oak Ridge actually got there a few months ago. And I'll kind of drive home that point. You know, we talked about that Japanese system, 36 teraflops, node level performance in 2018 on Summit. We can now hold that same computational power in our hand, in the palm of our hand, with one of today's newest graphics processing units. Okay, so that's how far things have come in the last 20 years. But basically, Oak Ridge was able to put together a system based on some of these technologies here recently. And using thousands of these, we're able to break the exascale barrier for the first time. So 1.1 exaflops this past summer. And what's really interesting is go back and revisit the power discussion. If we had tried to do this with 2009 technology, our power bill would have been 3,000 megawatts to get an exaflop of compute. Now, leveraging the latest hardware kind of paradigm shift, I believe Oak Ridge is seeing an exaflop for about 25 megawatts of power. So just a substantial reduction in the power requirements to get that compute that we're after. And so again, that's just kind of one of the many benefits of moving to a new architecture such as these. Where we've been the last couple of years, we've been preparing for Frontier and Aurora, a new exascale system coming at Argonne. We're going to continue that work and continue to engage with our users across the country. But really where I see our value is continuing to understand implementations of relevant motifs down to bare metal level so we can objectively understand the reason why we can get peak performance or may not be able to get peak performance. And that allows us to ultimately quickly identify technologies that we need to pursue or maybe not to pursue. And so that's where I think our research team needs to continue to have a big, strong emphasis. So finally, let me just wrap up there. Thank you again for having me. If you heard anything that kind of caught your ear or your eye, I'd be happy to hear from you. We are looking to expand our team and we are hiring. So please reach out if you saw anything you like. Thank you.